Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on confidence intervals for a mean. Let's get started. This here is the generic formula for the confidence intervals. This is on the AP Stats formula, so you do not have to remember it. I've shown you this slide before. This green part that I've shaded here is the margin of error. The margin of error consists of the critical value times the standard error of the statistic. And here's an example. My statistic in this case is X bar, plus or minus the critical value, that's Z star, and the standard error of the statistic is the population standard deviation sigma over the square root of n. Now, it is very rare that we know the standard deviation, the population standard deviation. So this formula right here gets little usage. When sigma is unknown and the conditions are met, the confidence interval X bar is given by this equation right here. X bar is our sample mean. S is the standard deviation over sample mean. N is the number of observations in the sample. And T star, is the critical value for the T distribution with n-1 degrees of freedom. And I'll have to explain that. The margin of error is proportional to 1 over the square root of n. So let's talk about the critical value, the critical T value, sometimes called T star. Because we are using S, our sample standard deviation, instead of sigma, the population standard deviation, we must use the critical T star rather than Z star. The critical T value measures how many standard errors we need to go from the mean to have C% of the area under the T curve with the specified degrees of freedom. Now, we've talked about the normal distribution, the binomial distribution, and geometric distribution. Now I'm going to introduce you to the T distribution. Actually, it's a family of distributions. The T distribution is similar in shape to the standard normal Z distribution in that it is symmetric, about 0, and has a single peak. T distributions have more area in the tails and less area in the center than does the normal distribution. The T distribution depends on something called the degrees of freedom. I'll explain that. And for very large samples, the T distribution approximates the standard normal or Z distribution. Now, the T distribution is a family of distribution, as I said. When discussing T distributions, you must always specify the degrees of freedom. So let's talk about that. To use the T table or the calculator, we must know the level of confidence and the appropriate degrees of freedom. The number of degrees of freedom, abbreviated DF, is the number of observations minus the number of constraints placed on the data by the calculation. And I know that seems confusing, but in this chapter, degrees of freedom will be n-1, the size of the sample minus 1. So why do we use T star and not Z star? Well, since we don't know the population standard deviation sigma, we estimate sigma by calculating S, the standard deviation of our sample data. However, we just can't substitute S in place of sigma in the formula for the standard deviation. Whatever value sigma might have, sigma is a constant. Not so with S, the sample standard deviation. The sample statistic S varies from sample to sample, introducing uncertainty into our attempt to model the sampling distribution of X bar. The increased uncertainty means that our margins of error need to be bigger to allow for that additional uncertainty. The T distribution takes this additional uncertainty into account. That is why we use T distributions. T distributions have fatter tails than normal distributions to take into account this added uncertainty. So here I've drawn two T distributions and the standard normal Z distribution. Okay, let's talk about the blue curve first. That is the T distribution for degrees of freedom 10. And you can see it has a fatter tail than the standard normal distribution. Then I have the green distribution. That's the t distribution with degrees of freedom 20. And the tails aren't quite as fat. And as my degrees of freedom increase, my t distributions are going to approach the standard normal z distribution. Now, as I said, the sample statistic S varies from sample to sample. The increased uncertainty means that our margins of error need to be bigger. By how much? Well, that depends on n, because as the sample size increases, that bothersome uncertainty, that sample to sample variability in S decreases, and the t model, the t distribution, looks ever more normal. You can see that in the graph. As n gets bigger, as the degrees of freedom gets bigger, the t distribution approaches the standard normal distribution. Now I have a problem up here. And this is the kind of pesky problem that you might find on a multiple choice question on the AP exam or on our quizzes or tests. Of the distributions shown, which has the smallest probability of getting a value less than 2? So we're talking so I've drawn on this graph here a borderline at 2, and we want to find the smallest probability of getting a value less than 2. So we're looking at the left side of the borderline. But that's kind of hard to think of. So I want to look first at the right side. Let's look at the blue side of that borderline. You can see that the standard normal distribution has the smallest probability of getting an outcome greater than 2. That is this small shaded area down in here. The green distribution has the next smallest, and the blue distribution, the t distribution with degrees of freedom 10, has the largest probability of getting a value greater than 2. Well, if it has the largest probability of getting a value greater than 2, then it has to have the smallest probability of getting a value less than 2. So our answer is the t distribution with degrees of freedom 10. This is what a t-table looks like. I have two t-tables right here. The t-table on the left is the one that is in your formula sheet. You'll have this table available to you when you take the AP exam. And as you can see, just look down that left column on the left table. Look on the left column. Go all the way down to infinity. And then go over to the confidence level for 95%. And you'll see that my critical t is 1.96, which is the same value as we would have for our z distribution. Let's go through a couple examples. Here's the first one. What critical value t star should we use in constructing a 95% confidence interval based on a simple random sample of size n equals 31? Well, the t distribution is a distribution, so on your calculator, you're going to go to Module 2, F5 for distributions, then you're going to select the t distribution, and since we know the probability and we want to find the location, we need to use the inverse t function. Okay, now on the calculator, on our Casio calculator, the inverse t function requires that we input the area in one of the tails. So to get the appropriate t star for a confidence interval, we need to divide the area in the tails by 2. Well, for the 95% confidence interval, we have 5% in the tail. So I divide that by 2 and I get 2.5%, or my area of 0.025. My degrees of freedom is my sample size 31 minus 1. So that's 30. I hit execute and it reveals that my t star is 2.042. That's the calculator method. I have put here the table method, but I'm going to encourage you to use your calculator because it's more precise, especially in examples like this one right here. What critical t star from the table should be used when constructing the 90% confidence interval based on a simple random sample of n equals 36? Okay, well, we're going to use our inverse t function again. My confidence interval, I'm looking for the 90% confidence interval. So the area in my tails is 10%. I divide that by 2, and I get the area in a single tail of 5%. So my area is 0.05. My sample size is 36. So in this chapter, the degrees of freedom will be 36 minus 1, or 35. I hit execute, and the calculator generates my T star. The use of the table becomes a little bit more difficult in this situation because degrees of freedom 35 is not on the table. Let's go on to the next problem. For large samples and the 95% confidence interval, the critical T value is approximately 2, or as I showed you on the table before, 1.96. So here are the conditions for performing a confidence interval for mean. The first condition is that the data has to be random. It has to come from a random sample or randomized experiment. If the data is not random, we really can't use it. We've got to start over. That's an important condition. Independent observations, or the 10% condition, when sampling without replacement, we need to check that the sample size n is less than or equal to the population size divided by 10. If that condition is satisfied, then we can use our formula for standard deviation or standard error. The last condition is the normal population or large sample. In this case, the population must have a normal distribution, or the sample size must be large. And here we're going to say that 30 is, again, the threshold. Now, we're going to relax the standards just a bit here, and I'm going to introduce this new condition here, or the new way of passing this test. If the population distribution has an unknown shape and the sample size is less than 30, we can use a graph of the sample data to assess the normality of the population distribution. So this means that you're going to have to, if we give you data and there's less than 30 observations, this means that you're going to have to draw a box plot, a dot plot, a stem and leaf plot, or a histogram, and you're going to look for, look at the last bullet point. If the sample size is less than 30, do not use the Z or T procedures if the graph shows strong skewness or outliers. So you're not going to use this procedure if your graph of the data shows strong skewness or outliers. The T procedure is a relatively robust procedure. It works pretty well, even if there's small departures from normality, as long as there's no strong skewness or outliers. Now, when sigma is known and the conditions are met, the confidence interval for a sampling distribution of X bar is given by this formula. But it is very rare that the population standard deviation is known. I mean, frankly, if you know the population standard deviation, then you should know the true mean. So this formula right here does not get a lot of mileage. The sampling distribution for a sample mean, when the certain conditions are met and the population standard deviation sigma is not known, then the sampling distribution of X bar has a mean equal to the population mean and a standard error is given by that formula. And here's how we interpret that standard error. It is interpreted as the typical distance between our sample mean and the true population parameter mu. And finally, here's our formula for the one sample T interval. When sigma is unknown and the conditions are met, our confidence interval for X bar is given by this formula. And I've already talked about that. The width of the confidence interval tends to decrease as the sample size increases, because you see that square root of n is in the denominator. How to analyze inference problems? Well, we're going to still use our four-step process, I for identify. C for conditions, C for calculate, I for interpret. In the identify part, we're going to want you to define your parameter and state the confidence level. In the conditions part, it is not enough to just state the name of the condition or put a check mark next to it. You have to use the facts of the problem to show that the condition has been met. And this may mean doing some calculations. Okay, so let's go through an example here. As part of their final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured 1/4 cup of water onto a hard surface and counted how many squares it took to completely absorb the water. Here are the results from their 18 rolls. Okay, so we have the data here, and we can see that the observations are less than 30, so we know we're going to have to graph that data to assess the normality of the parent population. Here's the question. Construct and interpret a 99% confidence interval for mu equal to the mean number of squares of generic toilet paper needed to absorb 1/4 cup of water. Well, the first step is the identify part. In this section, we want you to define the parameter and tell us the confidence level that we're going to use. We want to estimate mu equal to the mean number of squares of generic toilet paper needed to absorb 1/4 cup of water with 95% confidence. Now, in this case, the mu was defined in our problem, so it may not be necessary to define it again, but it's just good practice. Here are the conditions. We will construct a one sample t interval provided the following conditions are met, and that is the name of the procedure, one sample t interval. I want you to use that, mention that at the beginning of the conditions section. Random, the students selected rolls of generic toilet paper at random, so that condition is met. The 10% condition, well, it's reasonable to believe that there are more than 10 times 18 or 180 rolls of generic toilet paper, so we meet the 10% condition. Now, for our third condition, remember, our sample size was only 18 and we don't know the shape of the parent. So here's what we write. Since the sample size is small, I write n equals 18, and we aren't told that the population is normally distributed, we need to check whether it is reasonable to believe that the population has a normal distribution. So I graphed it, and there you have the dot plot. The dot plot on the right doesn't show any outliers or strong skewness, so it is reasonable to assume the population distribution is approximately normal. Now, again, you could have drawn a box plot or a stem and leaf plot or histogram, but what we're looking for is this. Does the dot plot show outliers or strong skewness? And if it doesn't, here is the conclusion that you need to make. It is reasonable to assume that the population distribution is approximately normal, because if the population distribution is approximately normal, then we can use our t distribution. That's the assumption under which the t procedure operates, that the population distribution is approximately normal. So we've met the conditions, we're ready to proceed. Now, here's where I want everybody to get out their calculator. Pause right here if you don't have your calculator. So let's go through this. The Casio calculator for the syntax for one sample t interval for the mean. Here we go. So from the main menu, enter the statistics module, that's number 2. And then we're going to press INTR, that's for interval. That's button F4. Then we're going to press T because this is a T interval, that's F2. And then we're going to press one sample because we're given one sample. So at this point, here's how you're going to input your data. Now, one way to do it is to put all of the data into list 1. And since you haven't done that right now, I'll show you another way. But the best way is to put the data into list 1 and then check F2 for list to make sure that we're using the list data. Input the confidence level, that's 0.99. List, since you have all your data in list 1, make sure it says list 1, and frequency 1. Now, suppose that you don't have a list of the data, but instead we give you the mean, the standard deviation, and the sample size. Then you're going to hit var and make sure then you input your variables. So this is what we're going to do this time right now. So let's the confidence level is 0.99, X bar input 24.944. That's the mean of the sample data that we got. Input X bar equals 24.94. SX, that's our standard deviation of our data. And so for that, input 2.8588. Our sample size is 18. Now, regardless of which method you input the data, the left or the right, you're going to get an output that looks like this. The lower bound is 22.99. The upper bound is 26.897. It tells us the mean of our sample, the standard deviation of our sample, and the number of observations in our sample. So you want to write down that lower and upper boundary. And here we go to our conclusion. I report that our sample mean is 24.94 and our sample standard deviation is 2.86. Now, because we are using a t-distribution, we must report the degrees of freedom. Always report the degrees of freedom with t-distribution. So degrees of freedom are n-1, 18 minus 1 is 17. And we also have to calculate t star. Well, actually, we don't actually have to calculate it, but I'm going to do it to show you how it works. I went to inverse t. Now I'm using the 99% confidence interval. So that means I have 1% left over. I split that into two tails. I get 0.05 in each tail. So that's the area. My degrees of freedom is 17. I hit execute, and that tells me my t star of 2.898. So now we go to our formula. On the left-hand side, I have the formula in symbols. You do not have to write that down unless you need it as a reference. What you do need to do is put the numbers from the formula, numbers from the problem, into the formula. So I put my mean of 24.94, my critical value of 2.898 times S, that's 2.86, divided by square root of 18. Now, I ran this through my calculator and I figured out that I get a mean of 24.94 and a margin of error of 1.95, which gives me my upper and lower boundary. So this is one perfectly acceptable presentation of your calculations. Now, I will tell you this. Reporting the t-value is optional. You can just put a t star in the formula instead. So I don't actually have to calculate 2.898 or put that number into my formula. I just substitute t star into my formula. That is acceptable on the AP exam. And finally, we need to conclude. That means we interpret our confidence interval. We are 99% confident that the interval from 22.99 squares to 26.89 squares captures the true mean number of squares of generic toilet paper needed to absorb 1/4 cup of water. And that's our presentation for today. Thank you for listening.